in propulsion from IIT Madras in the year 1989. He has got Masters in Management Science from Osmania University in 2005. And at present, AVMP Kangaraj is the SMSO, Senior Maintenance Staff Officer at WSC Headquarters, Subrat Park. Prior to his present appointment, he was Commandant AFTC at Bangalore. Then he was having a tenure of Principal Director of Engineering Air Headquarters, who was responsible for the total maintenance of the Russian fleet there. Then he has had a tenure in Chief Engineering Officer at Air Force Station, which is a very, very prestigious Air Force Station, 32 wing, Jodhpur. And then sometimes he was Commanding Officer, Air Armament Inspection Wing at Ordnance Factory, Jabalpur. And fortunately, he has worked with me at RCMA Koraput for about 3 years. He is having the varied experience of the DRDO organization as well as the DGAQA organization. He had the brief tenure in DGAQA Koraput as well as RCMA Koraput. Now he has specialized in aero engines actually. And he has spent his life, even if he is an SM also, if any aero engine problem comes, obviously he is the man to solve it or to give the guidance. He has spearheaded life extension program of Russian aero engines. His area of interest has been carrying out the defect investigation and aircraft accident investigation. During my tenure, when he was there with me at RCMA Koraput, really Indian Air Force and RCMA Koraput has got a lot of benefit about his way of looking the problems and giving the solutions. He has participated in a number of investigations and successfully resolved most of them. That is very much important. In present appointment, he manages the assets of the largest command of the Indian Air Force. We might have heard on Saturday we have inducted C-130J. He is the man actually behind this. I think with this background, I request AVM Kangaraj to take over as the chairman and to conduct the session.
Thank you, Mr. Gowda. Thank you, Mr. Gowda. Good morning, ladies and gentlemen, and welcome to this technical session on helicopters. We are already way behind, and I think we should not waste much time in the formalities. Let me get to the first speaker. We are having 3 speakers for this technical session. The first speaker is Dr. Prasad Sampath. Dr. Prasad Sampath obtained his bachelor's degree on aeronautical engineering from IIT Madras. Most welcome, sir. And his master's and doctorate degree on aerospace engineering from University of Maryland in USA. Since 1980, he has been associated with the design of helicopters. His involvement includes flight mechanics analysis, wind tunnel testing, ALH automatic flight control system, design and certification, and integrated architecture and display system. He was a chief designer of RWR and DC since July 08 to November 09 and is presently the general manager of the same division since December 09. Now I hand you over to him to speak on the design and development of ALH system. Over to you, sir.
Thank you. Here or there?
I can start from here.
From there?
Or from there. Your slides will be there.
A very good morning to all of you. As already stated, I will be talking about the light combat helicopter and how we went about designing this light combat helicopter. The talk would cover basically what's stated here. I'm not sure, is working consistently? Right. I'm going to talk about the background, the technology features, design and development, the way ahead, and a bit of summary to summarize the whole thing. First, to talk about the HAL itself, we have many R&D centers in India. We have centers at Lucknow, Korwa. We have a center at Kanpur. We have a center at Hyderabad. All of these are accessory divisions. And at Bangalore, we have two of the largest design houses. In fact, three, I should say. We added a new one this year, or last year. We have the Aircraft Design Center, the Rotary Wing Design Center, and the Mission and Combat Systems Center. Okay. Talking about the RWRDC, it consists of 433 designers and 170 plus 18 support staff who actually provide the manufacturing and assembly services. And you can also see the number of engineering graduates, and among them we have 238 postgraduates with masters and 3 with doctorate, and that includes me. Okay. We have a whole lot of capabilities. I'm sure without these capabilities you can't really design anything. We have the capability of making feasibility studies. We can do detailed designing. We are well versed in aerodynamics, stress, and vibration. Vibration is probably one of the more difficult areas, and we have a fairly good idea of vibrations. No aircraft is worth its salt without systems, and we are talking about not only avionics, we are talking about weapons as well. We do a whole lot of testing on the ground as well as in the flight, and therefore we build a whole lot of prototypes. And we then have to certify the product for its airworthiness. Currently we have, apart from the LCH, where we have the utility as well as the weapons version, we have LCH fairly advanced. We have LUH, which has come to metal cutting, and the future projects are the IMRH, which will start in the near future. A very graphical presentation of the kind of capabilities that we have built up in India. We started in 1965 through license production of Chetak, and then we went into the Cheetah. We designed the LCH starting in 1984. It's still going on. In 1998, we started the weaponized version. In 2006, we started the LCH. In 2009, we started the LUH. And we are hoping that somewhere in 2011 or 12, we will start the IMRH. Background. Why do you need the LCH? Basically, the Kargil, post-Kargil analysis showed that we had to equip ourselves with more capable weapons. Okay. And therefore, in 2003, we had an air staff requirement for a light combat helicopter. And the project was sanctioned in October 2006. Initially, the LCH started out in the first designs with a nose landing wheel, and we migrated during the design to a tail wheel landing gear. A whole lot of studies were done. There was a team which studied the pros and cons of these two configurations. And one of the single most important factor which decided for the tail was the fact that the nose wheel, when it crash lands, could affect the cockpits and the pilots as well. Okay. So it was decided then to go for the tail wheel landing gear. Based on that, we have built the mock-up, which was displayed in Aero India 2007. The scope of the project was to build one mock-up a breakaway fuselage. Basically, it establishes the integrity, structural integrity of the aircraft. You build the basic structure, put it in a rig, test rig, and then you subject it to the kind of forces and loads that the aircraft would see in flight. And you take it to its ultimate load. You see the structure, whether it can withstand or not. To do the flight testing and consequently the certification, the 3 prototypes were planned. TD1, which is flying, and you will see its display at the air show. TD2 will also be there. It will be on static display. TD3 is yet to be built, and basically it's spaced out so that all that you get feedback from the flight as well as other feedbacks will be incorporated in successive prototypes. So TD2 is slightly different from TD1, and TD3 we are expecting will be closer to the final production version. The roles of the LCH, it's a dedicated attack helicopter as opposed to ALH, which has got both utility as well as weaponized version. It has a defense role against UAVs. It can be offensive. It can support all the ground combat. It can do rescue. It can do an anti-tank and various other defensive roles as well. You can't have offense without defense, so it has a whole lot of defensive mission systems which are integrated onto this aircraft. The design objective is basically to meet all these requirements, and some of the things that are important on an attack helicopter are the high maneuverability, the high survivability, low vulnerability with stealth features. We'll talk about this in a little while. It has a high degree of crashworthiness. It's higher than what the ALH can give. It is both night as well as day. It has a high reliability, which is built in through design. These are some of the advanced technologies, but many of them are really taken from the ALH itself. The integrated dynamic system is common with the ALH, the hingeless main rotor, the bearingless tail rotor, anti-resonance isolation system, the ARIS, is also taken from ALH. What it doesn't have is the other vibration, active vibration control is not there on this aircraft because it doesn't have space. So the structure has been built in order that it does not vibrate as much as it would have otherwise. Okay, so you are paying some penalty in terms of weight. It also has a very advanced class cockpit. It has crashworthy seats, and of course it has the higher powered Shakti engine. In terms of survivability, what's fitted is you need to see that it has an IR suppressor. It will suppress the IR signatures emanating from the engine. It has dual engines, dual hydraulics, dual AFCS. Another thing that we have not done on the ALH, it has a pressurized cockpit, and it's going to be NBC safe. Okay. It has a narrow fuselage and flat glass panels. Basically, we are trying to reduce the glint. It will have armor protection, and it has a whole lot of flat surfaces, which you will see when you see the LCH. And basically, these are to generate low radar cross sections. It has a crashworthy tricycle landing gear. These are the kind of weapons that will be fitted on the LCH. You have an air-to-air, you have rocket, you have turret guns, you have air-to-ground missiles, EW suit, HPS, and of course data link and EO port. This is the kind of weapon configuration that it can carry, and there are 4 stations on the LCH. It's like a armament boom. It's different from the ALH. It can carry either 4 rockets or 2 rockets, 4 AM in whatever combinations. Then the weight is the criteria here. and nothing else. This is the power plant. It is slightly heavier than the 2B2, which was originally on ALH, and it has higher power. Of course, you know that with this engine now we are able to lift more than 200 kgs at 6 kilometers on the ALH. No other aircraft, helicopter can do that. The main rotor is composite. It's hingeless. It's the most agile helicopter in the world today because of this rotor system that we have on ALH and LCH. The tail rotor is also 4-bladed, and it's also composite, and it's a bearingless tail rotor. It doesn't have any of the mechanical bearings, etc., that are common in rotor systems, and this actually improves the reliability of the rotor. The transmission is called an integrated dynamic system. It not only houses the gearbox, but it also houses the upper controls inside that. It is considered to provide some safety in terms of fire when you're under fire. And at the bottom you can see the intermediate gearbox and the tail gearbox. They are same as on ALH. This is what the cockpit is going to look like. It has MFDs, it has standby instruments, and whatever. It's very modern, it's state of the art. The airframe, this is what the airframe is. This is the kind of airframe which you would put in the breakaway fuselage test. You would load this airframe and you will check for its structural integrity. The LCH, like the ALH, is very composite intensive. We use carbon, Kevlar, and glass. We also use metallic, especially when we are using the frames. And these panels which we are using on LCH, unlike ALH, they are actually metallic sandwich panels, metallic composite sandwich panels. The glass is Perspex. Something unique at HAL, we are changing over from the normal push-pull rods to a push-pull cable. Okay. And this is done to realize some weight reduction, and it also improves the maintenance, etc., using such high technology equipment. This is what the landing gear looks like, the main landing gear as well as the tail landing gear. They've all been tested for crash. This is what the vibration control that we have, and we also have lately installed on the ALH and also on the LCH what is called as the vibration monitoring. Okay. This will actually monitor all the vibrations that the dynamic systems are being subjected to, and based on the data that is recorded, we can actually look at the health of the dynamic system. It's basically something like hums. Okay, it is really the hums. In the design, we start normally with a feasibility study. We come up with some shape, we put it into the wind tunnel, and we do a lot of testing at the wind tunnel to ensure that the drag is minimum. We carry out weight, CG, etc. because unlike aircrafts, helicopters have a weight problem, and your payloads can be greatly affected if your weight is high. We did have this problem on the LCH when we started, and we have had to reduce from the initial estimates something like 350 kgs, which we have done fairly successfully. Aerodynamic analysis, vibration, we actually use finite element models to study the stress as well as the dynamics. We build cockpits so that the pilots, the test engineers, the maintenance agencies can look at these cockpits, and they will give us feedback on the ergonomics as well as the maintainability of this aircraft. This has been done. LCH is a very compact helicopter. We've had to push in things, whole lot of things, so space is at a premium, but we have tried to manage this maintainability in spite of all of that. This is just a detailed design. we have to study the structure. We have to study the systems that go on, where the system should be put, what is the kind of installation problems. We have to study whether there are interferences and all that, and then we actually release the drawings and start the prototype assembly. The design tools, of course, is the ambience that you need. At HAL now we are very clear that unless you provide the right kind of tools to the engineers, you may not get quality work. So we have a very sophisticated design center, a whole lot of computing facilities and computing tools. We use finite element models. We have what are called as, there's a team center, which there is a product data management software in that, based on which we can actually keep track of all the drawings, all the SOP, standard preparation. We can track changes, all that which is important to ensure that when you finally certify, you have all information with you. This is what you can do with the team center. You can actually design each component in 3D and then fit them all together to build it right there in your computer. When we do this design, we are also looking at the tooling, and even before the drawings are released, we would have already started building the jigs. And that's really what saves time. Okay. This is the kind of collaborative efforts we have used. For instance, a lot of these important control rods have come from our Nasik division. We have sheet metal parts which are done within Bangalore. We have identified and developed many vendors, and we also have our aircraft division where it can be done. Landing gear was fully designed at HAL, and it was fully built by Nasik division of HAL. The composites, of course, we have a very sophisticated composite division where many of the critical composite parts are made there. Many others are outsourced. No design can be done by an individual, and this is just not individuals together in an organization, but there is a whole lot of organizations which have to come together to make a product. And especially in aircraft industry, this is a must. So you can see that we've got Air Force, we have got Semilac, we have got DGA QA, we have got our own flight test center, AST, and other HAL units. And of course, we have various other people who actually make systems for us. This is again a repetition of how a prototype gets made. Okay, this is some of the kind of testing that we do. Okay, that's a landing gear drop test that will actually confirm that we have done the right crashworthy structure. We also have something called a shake test, where the aircraft is subjected to a certain amount of force at various frequencies, and these frequencies you have to ensure that the response of the structure is nowhere close to the rotating frequencies of the blades. Okay. We also had done some push-pull cable test so that you don't have surprises when you go into the aircraft. So all the aircraft was built. The aircraft is subjected to a whole lot of ground.
Back a little.
We actually test the various systems, especially the dynamic systems. This was what the inaugural flight of LCH was. Right. This is just a small table of the performance of the LCH. They are fairly good with respect to contemporary attack helicopters. This is what I was talking about. You don't build prototypes just to fly them and show them at air shows. They are very important sources of data and progressing the design to its final stage. One of the things that aerodynamicists will always talk about is the drag. And we also needed to improve the drag on the LCH. There are very many appendages that stick out on these aircrafts, and we found that through internal tests as well as through actual flight testing, we had a bit more drag than we wanted. And this has been corrected by means of two things. We have put some fairing on the tail rotor, tail landing gear, and the armament boom which you will see at the air show will not be there in future. We have converted them into a wing, and this wing is under production, and as soon as it comes, we will start using them. The drags are also affected by some of the scoops that you put on them, and on the LCH now, we have modified the scoops so that you have less protrusions on the aircraft. There's a main landing gear fairing as well. The other thing that we did was the aircraft has a certain attitude when it flies, and this attitude can be corrected by means of the horizontal stabilizer efficiency. We found that the end plates were providing a little more efficient horizontal stabilizer than necessary, so we removed it, and we found that the drag was reduced because of this, because the frontal area gets reduced. Okay. Am I taking more time, or it's okay?
Oh yes, I think another 5 minutes.
Yeah, I'm all done, I think. This is where we are today. We have actually, in the last 35 hours of flying, we have turned on the AFCS. And even without the AFCS, one of the beauties of LCH is that it's more stable than ALH. Okay. It's absolutely stable. The pilots were impressed with the handling of this aircraft. Nevertheless, we still have an AFCS on this, and this AFCS is the same as what we have on the ALH, because the rotor system is the same. We didn't find many surprises, except that during the roll, there has to be a certain retuning of the gains necessary because of the low roll inertia that LCH has when compared to ALH. TD2 is already built. You will see it on the thing. This is just a base paint. You will see some fancy painting on this aircraft. I would love for you to see this painting. It's not done anywhere else in the world, this kind of painting. TD3 will be available in February 2012, and BAF, of course, sometime before that, we would be testing the BAF. What's in front of us as far as LCH is concerned? We have to now, after getting the aerodynamics and the vibration right, we will go into the weapon system integration, and all of these, what is written there, will be done. It needs to be flown at high altitude, takeoff, landing, etc., and the kind of weapons that it can carry has to be established. And we have to do cold weather as well. High altitude doesn't necessarily mean cold. There are, in the areas where we fly, hot and high. Okay. It has unique difficulties in making helicopters fly in that environment. We also have taken up an indigenous development of the IADS, or the Integrated Architecture and Display System, and the AFCS at HAL itself. We have a division called MCSRDC, which will take up this development. We also have started a co-development of hydraulic actuators, and they will be designed and then they will be produced at HAL Lucknow. After that, we will be on the way to certifying this LCH. In summary, it's a totally indigenous aircraft. We've not really consulted anybody on this one like we did on the ALH. Everything is ours except the systems, because we don't have all the systems with us. But otherwise, the structure and everything is indigenous. And all this we could do because of the ALH experience. of course, as already indicated, the design and development was a collaborative effort between the various industries and the airworthiness authorities, the CEMILAC, as well as the DGA QA, and of course the users. Right. Then I thank you very much for listening so patiently.
If there are any questions, we would like to take on just one question, please.
Yes. Yes, please. I'd like to qualify that. You can't. It's not a classical wing. It's really a boom which has a aerofoil cross section to reduce the drag. Okay. We are not designing it to offload the rotor as such. We are only looking at the drag.
This will be permanently fitted, or it is only when you have to mount weapons it will be fitted?
Actually, the booms are removable. Absolutely no problem. I don't know if you can see it there, but they have 4 bolts. Each boom has 4 bolts through which it is attached at the hard point. It can be removed, but we are not expecting the LCH to fly without the booms. Okay. But if it's removed, it can still fly. No issue.
This helicopter will be on display at the air show, and most of you will be visiting the air show. It will be the ideal opportunity for you to probably see for yourself, and that time Dr. Sampath will probably be available to clarify some more issues. Unfortunately, due to paucity of time, we are unable to take on more questions. I'm sure you will find more time during the interaction, during the lunch hour. Thank you very much, Dr. Sampath. It was a very interesting talk.
Thank you.
And